In, in this video, I wanted to show you an alternate way to map the port signals in my top level module to my constraints file. So I'm going to do this in a somewhat more elegant fashion. So here I have my original MUX 4 to 1. I have my 4-bit input X, my 2-bit selector, and my output Y. And my problem was that I wanted to map the 4 bits of X to, let's say, the rightmost 4 switches on my basis board. And then I wanted to map my 2-bit S to the 2 switches immediately to the left, and then the output Y would be mapped to the LED. So the way that I did it last time was good and it worked, but it was slightly inelegant. So what I'm going to do is I'm going to create a new module, and the sole purpose of that new module will be simply to map the port signals from my 4 to 1 MUX to port signals that are already in my constraints file. So again, I'm going to use that same methodology where I don't have to change the port names that are in my constraints file. Rather, I only have to comment or uncomment them, typically uncomment. So what I'm going to do is create a new design source. And I'm going to call this module top. Why? Because it's a top level module. So I can only ever have one top level module. That top level module, what distinguishes it from other modules is that its ports are directly mapped to inputs and outputs on my board. So I'm going to create a new file, and I'm going to call it top. And I'm going to finish. And it's going to ask me here. Now, I don't have to decide right away. So let's say I'm unsure. I mean, you can always cancel in this step, and then you can add these manually. So let's go ahead and do that. So I'm going to cancel. And here I'm going to create my module called top. And I'm going to list my port names here. Now, what do I need as ports? So I already said ideally what I want to do is I want to map my 6 switches to my inputs, and I want to map one LED to the output. So I'm going to use the same rationale that I did last time. So remember that I did that weird thing where I defined the LED as a vector of length 1. So I'm going to do all that again. I'm going to define my input. So it was 5 to 0 switch, and output 0 to 0 LED. And the only thing I'm going to do in the module, like its only purpose here, is to instantiate my 4 to 1 MUX. So what I like to do is basically I'm going to take the whole module declaration here with all the port declaration, so all the top level signals from my 4 to 1 MUX. And usually what I like to do is just paste it in here and then just kind of block comment it. So that way, if I'm doing ordered instantiation, so recall that ordered instantiation requires me to know in which order the signals are specified in my module declaration. So here they're X, S, and Y. So in order to use ordered instantiation, I like to put my module declaration here so that I can at a glance see the order of the signals in the port list. So I'm going to start with my module instantiation. So it was called a MUX 4 to 1. I'm not going to give it a fancy name. Maybe I'll just call it M. And my first signal is a 4-bit vector that maps to X. So these are going to be my rightmost 4 switches. So that's simply going to be switches 3 to 0. My selector, so I'm doing this now, my selector is going to be the leftmost two switches in my range. So that's going to be switches 5 to 4. And my output Y is simply going to be my lead. I want to say actually something important here. So I said lead. Now, when I do not specify a range, so this probably isn't the best example simply because lead is only a single bit wide. But if it was multiple bits wide, so for example, switches, if I just use the signal name switches, it is inferred that I mean the entire width of switch. So I don't always need to say switches, let's say 5 to 0 or lead 0 to 0. I could just say lead, and it's understood that I'm passing all the bits in that vector. So here you have it. So this is my whole top module. And I'm going to go take a look at my constraints file just to make sure that it matches. And so let's see. So I have switches 5 to 0 uncommented. And now I have lead 0 uncommented, and that is it. So I'm going to go ahead. Actually, what I want to point out now is if you look at my hierarchy, my module hierarchy in design sources, now I see that my top module is on top, right? Hence the name. And it's bolded, so it's denoted in bold. The module name is in bold. And then under it, I can see the hierarchy of modules. So I see that my top module instantiates my 4 to 1 mux. I've called this instance M. And my 4 to 1 mux instantiates 3 2 to 1 muxes. And their identifiers are mux 0, mux 1, and mux 2. So I'm going to go ahead and generate the RTL schematic just so that I can make sure that everything is correct. And what do I see here? I see my mux 4 to 1. It has 2 inputs and 1 output. At a glance, I can see my output is mapped directly to my LED, so I know that's correct. What about my switches? So switches 5 to 4 are mapped to my selector input on the mux, and switches 3 to 0 are mapped to my X input on the mux. So I can be confident that this, in fact, will implement correctly on my board. Okay, so the next thing that I want to show you, and this is going to speak a little bit to we're going to touch on a few new concepts here. So the first concept that I'm going to touch on is the concept of simulation. Let me explain what simulation is. I mean, I think we're all familiar with simulation here. So it's just a way for me to simulate my circuit, view the waveform in software, in Vivado, make sure that my outputs correspond to my inputs, they correspond to the design, and I'm basically getting what I want. It's just kind of like a sanity check, a way for me to test my circuit prior to implementing it. So, and I can test it with many different input conditions. So I'm going to show you how that works. Now, in order to run a simulation or create a simulation file, I need a few more concepts that we haven't learned yet. So the first one is, and what I'm going to do is I'm going to contrast it with what we've been doing up until now. So I'm going to show you, for example, my 4 to 1 mux. So everything is what's called concurrent. So everything I'm specifying here in my 4 to 1 mux, it doesn't matter what order I put them in. So by convention, of course, I didn't mean to do that. So by convention, I put my wire declarations up top, and then I instantiated my 2 to 1 muxes in this order just because that made sense to me. But it wouldn't have mattered if I had instantiated them in a different order. Another thing that wouldn't have mattered is, for example, in my 2 to 1 mux, I only have one assigned statement. But if I had multiple assigned statements, it wouldn't matter in which order I put them. This is like wiring things on a breadboard, right? Like it doesn't matter in which sequence I wire them. The end result is, as long as they're all wired, it is going to run, and the signals are going to travel through the circuit at the speed of light from the source to the output. And all the signal, everything is going to run concurrently. So anybody who's ever coded in a high-level programming language knows that's not how this works. In a high-level programming language, it's much more difficult to design things to run concurrently or in parallel. And in fact, a microprocessor processes instructions sequentially, one at a time. And so I can have this functionality in Verilog as well. So I can kind of like fake it a little bit. So in Verilog, I can have what's called procedural programming. So again, I'm going to contrast procedural with concurrent. Concurrent, where everything's happening all at once in parallel, and then procedural, where it really very much matters the order in which I assign values to signals. So the other thing that procedural programming in Verilog allows me to do is, a few things, but one other thing that it allows me to do is it allows me to use logic, so logical constructs that you may be familiar with from high-level programming languages. So what's called a behavioral specification. I can specify the behavior of something based on logical conditions. So for example, so again, for anybody who's ever coded in a high-level language, I have conditional statements like if, I can have loops, all those things are possible, but again, only within a procedural programming block, which I'm going to explain to you how to use. And we're only going to start with one, okay? So there are two kinds of procedural programming blocks that we'll use in this course, and we're going to start only with one of them, which is the simplest. And finally, the third thing that I can do in a procedural block that I cannot do. So far, everything we've done has been combinational. All our designs have been combinational. But if I want to have a sequential design, so I want to have something that has some kind of memory. So for example, as you know, a flip-flop only changes value at the pulse of a clock. It's synchronous with a clock. So until the next pulse of the clock, the output sort of retains the memory of what it was previously. And this is similar. This is actually like a straightforwardly the same concept as what I can achieve in a procedural programming block in Verilog. So I cannot achieve sequential designs or behavioral specifications in concurrent programming the way we have learned it so far. So I can only do that within a procedural block. So I'm going to start I'm going to demonstrate all these concepts with simulation. So the first thing that I'm going to do is I'm going to add a new simulation source. So when I add the source, I want to make sure that add or create simulation sources is checked. So it's not a constraint or a design source. I'm going to click next. I'm going to create a file. And by convention, like I call the file, the simulation file, you can call it your test bench or TB, which is not tuberculosis, but test bench. So I'm just going to call it TB. In fact, if I want to get more specific about it, it's my mux 421 test bench. If I really want to get specific, I'm going to click OK. And the module that I'm testing is my device under test, or DUT. So I created my file. I'm going to finish. I'm not going to have any inputs. I'm going to click OK. Yes, I do want to use these values. And now it's going to create a new simulation source called mux 421 test bench. However, notice that I still have top as my top module, even under simulation. But under simulation, so the whole point of this top module was to implement it on the board. I'm not going to be able to simulate with this file. So what I'm going to do now is I'm going to make this my new test bench. I'm going to make it my new top module, but only within my simulation sources. So if I go back, this has not affected my design sources. What gets implemented on the board is this, and then what gets simulated is this. And they can have different, I can have different files. I can have different simulation sources than design sources. But be careful, because what I'm simulating is not necessarily what ends up implemented on the board. What gets implemented on the board is specified by this here, the design sources, specifically by the top module here, which maps directly to my board I/O pins. So I'm going to go ahead and create this. The first thing that I'm going to draw your attention to, actually, in my MUX 4:1 is this timescale directive. So that backtick over here, this backtick, indicates a timescale directive. And we've never really talked about this before, so I'm going to explain to you what it means. So the first parameter, 1 nanosecond, is the time step for simulation. And the second parameter specifies the how fine-grained my simulation is. So, so what I'm going to do, I'm going to go back to my MUX 4:1, and I'm going to give you some general rules here. So the first general rule is that in a simulation file, I have no inputs and outputs. So in my top level simulation file, I have no input and output ports. I'm not specifying any input and output ports. Now, what I want to do here is I want to instantiate my device under test, which is basically my 4:1 MUX. But how I'm going to synthesize that is a little different. So I'm going to explain to you my approach to simulation. So in my approach to simulation, what I want to have happen is that every, let's say, 500 nanoseconds, I want to change the values of my inputs and observe the outputs, okay? Now, in order to do that, that means that my inputs have to retain the same values for 500 nanoseconds. And a thing that I know retains its values is called a register. So that's why I am going to introduce to you a new type, which is called a register type, reg. So I am going to declare a register for my X values. So again, the range comes before the signal identifier. And my second input for my MUX was my my selector S, which was 2 bits wide. So that's this. And oops. And finally, the only other signal in my MUX 4:1 declaration was the output Y. So all my inputs are declared as type reg. That's the general rule. All my inputs are declared as type reg because I'm going to vary them. I'm going to change their values, but only every, let's say, 100 or 500 nanoseconds or something like that. So my outputs are just going to be declared as a wire, my output Y. And now I'm going to instantiate it. So this is very simple. I'm going to call it my MUX 4:1. I'm going to call it DUT is the identifier that I'm going to give to it because it's my device under test. And I'm going to, again, just pass it X, S, and Y, semicolon. So far, nothing too new here except the reg keyword, which again, I'm using only for my inputs. So only for the inputs of the device under test, the module that I'm testing, that I'm instantiating here. And now another new thing is I'm going to declare a procedural block. And this procedural block is going to be called initials. There's another one called always, and that's different, and we're not talking about that yet. So that's going to be more for synchronous designs. But for the purposes of simulation, I'm going to use the initial block. And after initial, I have to indicate the beginning of the initial block with the keyword begin and the end of the initial block with the keyword end. And everything in the middle is going to be my simulation. So I'm going to tell you how this works. So the first thing that I want to do is, let's say I want to test all possible values of S, of the selector S with different values of Y, of X. Or maybe I'll do the same value of X. Let's make things simple. So my X initially at time t equal to 0 is going to be equal to, so I'm going to assign it a value, but notice what's different here. So this is something important. If I declare a signal as type reg or register, first of all, I can only assign its value within a procedural block. The only procedural block we know so far is the initial block, but there will be another one we learned called always. So its value can only ever be assigned within a procedural block. And second of all, I don't use the assign keyword. I simply assign it a value using the equal operator. So those are two things that are different about a register type. Okay, so initially my X is going to have the value, it's 4 bits, so it's going to have a 4-bit binary value. I'm going to call, I don't know, let's say 0, 1, 1, 0, let's say, okay? And actually that's not going to change. And then I'll just assign S an initial value. So let's say that S is, S is 2 bits wide, hence this, and I'm going to give it the binary value 0, 0. So I would expect my output Y, so again, recall that when S is 0, my output is going to be the 0th or least significant bit of X, which in this case is this guy, which is 0. So I'm going to observe the output in my waveform window once I conduct this simulation and make sure that this is in fact the case. So moving on, I'm going to do something else. So now I want to say retain these values for X and S for 100 nanoseconds. So and at 100 nanoseconds or 100 nanoseconds later, that's what this means. So it's hashtag 100 means 100 nanoseconds later. How do I know it's 100 nanoseconds? Because look at my time scale. So my time scale here is 1 nanosecond. When I refer to hashtag 100, I'm referring to hashtag 100 of these 1 nanoseconds. So after 100 nanoseconds, now I'm going to let X stay the same. So if I don't specify a new value for X, it'll just retain the same value. It's a register. So if I'm not specifying a new value, it's just going to retain the same value. But after 100 nanoseconds, now S is going to have a new value. And that new value, I don't know, let's do 0, 1. So what I'm going to expect to see in my waveform window is that my output Y is going to be equal to 1. Why? Because when the selector has value 1, the output Y is going to select this bit of X, the bit 1. So after another 100 nanoseconds, I'm going to assign S another value. I'm going to give it the value 1, 0. So again, what will I expect to see in my output waveform? I'll expect to see Y equal to 1, which is this bit. And then finally, after 100 nanoseconds, another 100 nanoseconds, I'm going to give S a new value, and that new value is going to be 1, 1. Oops. Okay, and I'm done here. This is my whole simulation file. So again, I just actually want to be clear. I could have put this on a new line as well. It doesn't matter. So if I had another statement here, I could have put it on a new line. So I'm going to start my simulation. So I'm going to run behavioral simulation is the one that I want. And in fact, I actually realize now I should have changed some simulation settings. So I'm going to do that after, because basically I want it to run for, let's say, 500 nanoseconds in total. But anyway, it doesn't really matter. So first thing I'm going to do, I'm going to zoom to fit. And let's look at the output here. So I can expand each of these. In fact, I'm going to float this window. Let's take a look at it here. X, as I can see from here, X stays the same. So these lines mean 0, and then these guys mean 1, are the value 1. X stays the same. So X doesn't change throughout, right? Which makes sense because I never change the value of X. But my selector does. So my selector starts at 0, 0, then 0, 1, 1, 0, and 1, 1, which is decimal 0, 1, 2, and 3 respectively. And now let me look at my output. So, and I can, of course, I can expand to see each individual bit. But let me look at my output here. So my output here is Y. So initially, when the selector is 0, I expect my output Y to be 0. Why? Because the value of X0 is 0. But when my selector has value 1, I expect Y to be equal to X1, which is 1. And in fact, that's what happens. It stays high here. And then after another 100 nanoseconds, recall that I changed the selector value. So that's happening over here. So the selector value is now 210. But actually at X2 is still high. So the value of my output remains high. And then finally, it goes back low simply because the value of the selector is 1, 1, or 3. And that means that my output is going to be equal to X3. And in fact, that's what I see here. So this just kind of lets me have a sanity check. Is my circuit working the way I want? It allows me to test it with a whole bunch of different values. I could do this in actually a much more efficient way, as I will show you later. I can just kind of loop through and change the values, increment the values of S by 1 until I've gone through all of them. So it's not so onerous when S can only take on 4 possible values, but let's say I had a 32-bit S or something like that, then I could do this programmatically very easily. I could test all 2 to the 32 possible values for S if it was a 32-bit wide vector. Very simply in just, maybe 2 lines of code. This is it. So this is how I simulate and test a file. So I'm going to close this off and I'm just going to review with you a little bit again. So what are the new things that we learned? So we learned how to do simulation. We learned, in fact, that when you simulate, the top level simulation source is not or does not necessarily have to be the same as the top level design source. And if I'm simulating, in fact, they shouldn't be. So notice here that this is the file that I'm simulating, which is my MUX 4:1, or the module that I'm simulating, which is my MUX 4:1 test bench. So it kind of replaces the top module here in that it instantiates not the top module, but the 4:1 MUX. So the same thing that the top module does, the simulation file does as well. So they're directly analogous. One does it to map the MUX 4:1 to the board pins, and the other does it to test different values of inputs and view them in the waveform window. So finally, here's my device under test, the guy that I'm testing, the module that I'm testing, which is the 4:1 MUX, and it has, and the 4:1 MUX, like here, instantiates it's the same module. It instantiates 3 2:1 MUXes. I have the whole hierarchy here. And in fact, this is never used in simulation. So there you have it. So again, my rules. My simulation module declares no inputs or outputs, so no input or output ports in the module declaration. It's empty. Finally, so I'm going to instantiate the device that I'm testing or the module that I'm testing. And all the inputs to that module I'm going to declare as type reg, and all outputs will just be wires. Finally, I assign the values of my reg signals within an initial block, or, well, in general, the general rule for this is that registered signals have to be assigned within a procedural block. But in this case, the procedural block that I'm using in a simulation file is always going to be the initial block. At time t equal to 0, I am just assigning them values, again, without using the assign keyword. So that's different between a registered signal and a regular wire. And then every 100 nanoseconds, I assign the selector a new value. And because I have not changed the value of x, it remains the same. So that's it. That's all I wanted to show you.